Damn it. There we go. Hello, Mr. Ritz. I'll be back in a second. Have to go get something.
Okay.
Be sure and put your name in chat. And do not use direct message. Otherwise, I can't. It
Gotcha.
won't show up when I take roll.
Okay. Gotcha.
Which is after class, I download stuff from Zoom, and one of it is the chat. And for some bizarre reason, Zoom has quit saving the direct messages.
Oh, true.
I got get my coffee. Oh, damn it. That's exactly what I was trying to avoid. Hello. Just spilt the coffee. Clean up on myself. Fortunately, I did not get any of the electronics. Well, I did, but it didn't go into the electronics. So my wife would say I was a slobbo. Yeah, coffee's still a little hot, so you're hearing me slurp. Okay. Oh, wow. I'm supposed to have 12 people in this class. So far, we have 5 people up. Go and put your name in chat. Do not direct message me, because I discovered the other day Zoom no longer saves direct messages in the chat when I pull it up. So I don't know what the deal is with that, but anyway, Yeah. All right. Please put your name in chat if you haven't already done so. Do not direct message me with your name because it won't show up in the attendance. What just happened over here? Oh, that's what I thought. Okay. Yeah. Please be sure and put your name in chat if you haven't already done so. And do not direct message me with your name. During class, if you want to ask me a question, go ahead and direct message me. But if you'd rather not use the if you don't want people to know you're asking a question or making a comment, or you have personal questions. But as far as attendance, do not use direct message. Okay. We got any questions about anything about MyLab or anything? I don't rightly know. Oh, we're only 9 slides into the PowerPoint, so that's really not enough to. Damn it. Okay, here we go. It's not syncing. It needs to. Oh, there it is. Okay. So let me see how many people we got. We got 13 people in, and I think there's, yeah, that's right. Everybody's here. Yay. That's easy. So, well, actually, we're going to have another person add to the class. I sent them a link, but they're not. I guess they didn't get the email in time. Well, I sent it 10 minutes ago, so no wonder she hadn't gotten it. But anyway. Okay, if there's no questions, I'm going to go ahead and go straight into the material. Which means I pull this up. I get the zoom back up. And I pull, oh, yeah, you were supposed to be over here like that. Oh, yeah, like that. No, 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 no. Stupid thing isn't doing it the way I want it to. All right. Oh, I'll find my Zoom windows again. Okay, here we go. And I go to advanced and I do this. And now I adjust the screen again. Okay. That. And there's that. Okay, and I believe this is a slide we ended on. We're talking about functions. What makes a function a function? Let me do something else over here so I can see everybody's lovely face. Oh, yeah, that reminds me. I like people that be on camera. Can't necessarily force you to be on camera, but I like you to be on camera. If you're a high school student, I say so I can point and laugh at you. But anyway, yeah, ninth graders don't appreciate that joke. I used to post when I was in the classroom. I used to teaching high school. I used to posted my joke of the day, and nowadays they're called dad jokes. Back then they were called stupid jokes. And after a while, a number of students would realize that they were stupid jokes. And I say, Mr. Reed, those are stupid jokes. And I say, yeah, I love stupid jokes. That's why I teach. Yeah, okay. A couple of y'all got that joke. I would have maybe 2 students out of the class get that joke. And they'd start laughing and everybody go, what was so funny? And so anyway, I used to have fun with my students, drive them nuts. The eyes rolled so hard. Anyway, okay, we were talking about what a function is, and I'm going to write down my definition of function. A function is a relation. And if you remember, a relation is just a set of ordered pairs. So instead of saying relation here, you could say set of ordered pairs. It's a relation where each x value each member of the domain, I spell value right. I don't know what I was spelling. Each X value is paired, because it's an ordered pair, is paired with, it's got to be doing this on me again. Yeah. It's done to this to me about 3 times today. So that was the 4th time I'd done it. Is paired with exactly important word, exactly one Y value, or one member of the range. Or you have, I think the textbook uses, you have a set X and a set Y, and you have each member of set X is associated with exactly one member of the Y, set Y. But this is so you have X and Y. It's an ordered pair. X always comes first. Students would ask me, 9th graders would ask me, how do I know the X goes first? And I said, do you know your alphabet? You'd be surprised how many of them said no. Or maybe not. Anyway, so that's what we're looking at. Okay. And this is an example of a set. This set going to this set. This is an example of a function. This is a relation. You have pairs. You have the X values paired with the Y values. Each X value is paired with exactly one Y value. You could use the word only instead of exactly, and it conveys the same thing. It's just exactly is more emphatic in its desire that X only has one partner. The Y value can have multiple partners. If you look over here, the toy company and the Good Locker have the same price on the Magic Ball, the Magic 8-Ball Retro Edition, but Good Locker only has one price for their Magic 8-Ball, and Toys and Company only have one price. So each seller here only has one price for each of their for that particular item. So that's what makes it a function. First of all, that it's a relationship between two sets of things, and secondly, that how they're paired up. There's only one Y value for each X value. Now, that doesn't mean the Y values can't repeat, but the X values do not. The repeating aspect here is an effect, not a definition. Okay, so if you will be asked several times on exams, what is a function? And if you say it's where the X values don't repeat, that is not the definition. That's an effect of the definition. So that's what happens because of the definition. So it's not a definition. Oh, come on, you're supposed to move. There we go. Oh, no, not yet. There we go. All right. And yeah, okay, so that's what they're saying here. The domain, which is the X values, the domain is the name of the companies, and the Y values is the prices. Okay. So here we have 3 sets of ordered pairs. Some Some might be functions, some might be just a relation, which is which. So is letter A a function? So you go through and you look at the X values. Are they paired with only one Y value? One is only paired with 5, 3 is only paired with 9. 5 in the X position is only paired with 1 in the Y position, and 9 is only paired with 2. So yes, this is a function. Right? Letter B, is that a function? Please notice that the 5 in the Y position repeats. That is okay. But using that effect, that if it's a function, the X values won't repeat. So when you list the ordered pairs, if the X values repeat with different Y values, then it's not a function. So 2 is only paired with 6. Each one of these is only paired, each number in the X position in the X coordinate is only paired with one Y value. So letter B is also a function. If you look at letter C, I do this, but I'm doing the second part first. I don't talk about the domain and range yet. I like to say, is it a function? Because that's the main focus here is it a function? Yes or no? And then domain is the X values, range is the Y values. So -5 shows up twice as an X value, but is it paired with the same number in both cases? Yeah, no. In the first case, it's paired with a 1. In the second case, it's paired with a -3. So 1 and -3 aren't the same number. So this is not a function simply because of that. It's just a relation. Right. So if we did a Venn diagram, here we have all relations. And a subset here, so it would be totally inside, is functions. For it to be a function, it has to be a relation to begin with. All functions are relations, but not all relations are functions. Okay. So on letter A, the domain is all the X values. So on letter A, it's 1, 3, 5, and 9. And for the range, it's all the Y values, which is 5, 9, 1, and 2. Notice they listed the numbers in chronological order, not in the order they appeared in the set. But notice I said that the range was 5, 9, 1, and 2. You can list them as they show up. That is fine. Here, they just went ahead and listed them least to greatest. On letter B, 2, 5, 7, and 1. That's the domain. And the range is 6, 5, 15. 5 showed up twice, but when we're writing the range, we're only listing numbers. So if something shows up more than once, we don't want to know how many times it shows up. We just want to know what shows up. Well, 5 showed up, so I only put it in once. And that's what they did here. So it was just 5, 6, and 15. And the second one here, the last one here, -5 showed up twice in the domain, but we just list it once. The -2 gets listed, the 2 gets listed, and the 3 gets listed. And I think in the Y values, none of them repeat. So it'd be all of those. Yeah. Oh, what happened there? Anyway. Okay. So is this a function? Is this equation a function? If I put different numbers in for X, will I ever get the same number for Y? Or will I get different numbers for Y for the same number X? Because of how I'm changing X, a single number will only give me one outcome, right? The equation tells us you take an X input, multiply it by 3 and add 7. For any input X, these operations yield only one Y value. So it's an equation. There's no number I can put in for X that will give me two different values for Y. Okay. And it's a linear equation, which means it's the equation of a line. It is a function. And if an equation of a line is a function, then we call it a linear function. There are equations of lines that are not functions. An example would be x equals 3, because that's a vertical line. On a vertical line, all the x values are the same. X values can't repeat, so it's not a function, but it's still a line. Okay. So the trick here is to solve for y. If you can solve for y and you just have y equals some expression involving a single x, then you're good. But doing this here, all right, we're going to solve for y. So that means we're going to subtract 6x from both sides and then divide both sides by 3. So they have, I would do it a little differently than they do it. X plus 3y squared equals 2. And we have 3y squared equals, and I would write it as a negative 6x plus 2, which is fine. And then you divide by 3, so you get a negative, no negative, Thomas. Y squared equals a negative 6x plus 2 being divided by 3. I would write it as a fraction. The whole thing is a fraction. But what they did, they wrote it as the sum of two fractions, or the difference of two fractions. But anyway. And then you take the square root, right? Taking the square root, realizing that the square root of 4 is 2 and negative 2. So you get a plus or minus 2. So that's two different numbers. So here, when I take the square root, I get a plus or minus the square root of a negative 6x plus 2 being divided by 3. So I wrote a 2 down there. I don't know. Okay. The plus or minus means I get two different numbers. So when I put a number in for x, I get two different numbers. I get a positive number and a negative number. So that means the x is going to be paired with two numbers. So that makes it not a function. All right. For the values for which x is less than negative, less than 1/3, two values of y result. Why did they say x has to be less than 1/3? Question. Can I take the square root of -4? In the real numbers, can I take the square root of a negative number? All right, let me state it this way. The square root of negative numbers exist, but are they real numbers? And the answer is no. Right? This gives me 2 times the square root of -1, and we have notation for the square root of -1 is the letter I. So we say that the square root of -1 is being represented by I. Mathematicians love notation, and mathematicians are inherently lazy. So if they can come up with a symbol that represents something we don't have to write so much, they'll do it. So instead of using the word square root, we have this symbol. Instead of saying the square root of -1, we use the letter I. And it's usually italicized. Some textbooks put it in boldface. Okay, or some different font.
Sir, correct me if I'm wrong, but this I stands for imaginary number, right? Just meaning.
Correct.
Okay. Make sure.
And that's where we get the name real numbers from. And imaginary numbers. Back when somebody proposed the notion of the square root of negative numbers, the powers that be in mathematics says, no, you're wrong. They don't exist. They only exist in your mind. They're imaginary. These are the real numbers. And that's how come we call them the real numbers and the imaginary numbers. Yes. Okay. So that's so what's underneath the square root symbol, and we're only dealing with the real numbers right now. So that means whatever's in here has to be greater than or equal to 0. So that means the -6x plus 2 divided by 3 has to be greater than 0. So you solve for x. That means you multiply both sides by 3. 3 times 0 is 0, and 3 times this just gets rid of the denominator. So it's 6x plus 2 greater than 0. I subtract 2 from both sides. So now I have a -6x is going to be greater than a -2. And now we're going to divide both sides by a negative number, -6. And what happens when you divide an inequality by a negative number? The inequality changes direction. So now a -6 over a -6 is 1. So you have 1x is going to be less than, because it has to change direction, less than a positive 1/3, because negative over negative is positive, and 2 over 6 reduces to 1/3. That's why x has to be less than 1/3, because whenever I put a number in here, I have to end up with a positive number or 0. Okay.
Sir, my bad. I'm a bit confused. The 6x plus 3y squared equals 2. That's the same equation as the one on the right.
Yeah. This here is
Yeah.
saying the same thing this is saying. Let me get my pointer up. So, okay, because I could write it, how they wrote it was as 2 minus 6x, and then they divided by 3. So you're going to divide each one of these by 3. So that gives you 2/3 minus 2x.
Okay,
These two mean the same. They give you the same numbers.
yeah,
Okay.
okay,
They just look different.
okay.
So this isn't a function because we get two different y values for a single x value. If I put, what is it? If I put 1/6 in for x, that means I have 2/3 minus 2 times 1/6. It's going to be square rooted, plus or minus. And so that's going to be plus or minus 2/3 minus 1/3, right? Because and then you get plus or minus the square root of 1/3. So you get a positive square root of 1/3 and you get a negative square root of 1/3. And those are two different numbers for the same x value. So that makes it not a fraction. All right, now to find the value of a function, this is something you've been doing all along. It's just now you're going to be looking at different kinds of notation. All right, a function in Algebra 1 and Algebra 2 in high school, they sometimes referred to this type of a machine for a function where you put something in and you get something out. Okay. Now, when you put something into a function, you get only one result. Okay. So that's what we're talking about. So you put something into the function and you do something to that number to get your number to get another number. Okay. It accepts only numbers from the domain of the function. All right. So you can't. So like on that previous example, we can't use numbers that aren't less than 1/3, actually one less or equal to 1/3. Okay, because 1/3 gives us 0 here and square root of 0, 0. But anything less than 1/3 works in there. So if I put 1 into this function, I can't get a real number because it's not in the domain. So that's what that first statement is saying. And for each input, there is exactly one output, which is the definition of a function. Okay. So for a function, y equals f of x, right? So now we're talking notation again. And this is function notation. And it said, and we say it f of x. So we're doing some function on x. And the y, f of x just means the y value you get. Now, the definition of the function is what f of x equals. So some function of x, something being done to x. So like 2x minus 3 or 17x squared plus 3x minus 47. So I could have different functions. And if I'm talking about different functions at the same time, I'm just going to give them different names. So we can say this function name is f, and then I have another function's name that is g, and that's just 2x plus 5. So if we're talking about multiple functions, we can give them different names simply by changing the letter of the function. We're still using X as the independent variable where something happens to X, and the value you get from the function gives you your Y value, which is the dependent variable, because its value depends on what X is. You choose the X to put in there, and it predetermines what the Y is going to be. So Y is dependent upon the X you put in. Realizing that just because 3 gave us 5 doesn't mean 5 won't show up again as a Y value. But it does mean that 5 will only be paired with 3 will only give us 5. All right, that's a word I will use a lot. We talk about the argument of a function. Well, that's what we're using in the function. That's what we're doing things on. Okay. I think we start talking about logarithms later on. Right. The argument is what's inside the parentheses here. The log is the function, and the argument is the number of X, what we put in for X. So the function is what's happening to X here. Now, to evaluate f of X plus 3X, this f of 3 means we're going to put 3 in place of X in the function. So f of 3 means I'm going to be doing 2 times 3 squared minus 5 times 3. So this gives me 2 times 9 minus 15. So I get 18 minus 15, which is 3. So f of 3 equals 3. So in that function, in that what they're asking for, f of X plus f of 3, I just replace f of X with the definition of f of X. The definition of f of X is 2x squared minus 5x, and then I'm going to add what f of 3 is. F of 3 is 3, so boom, I'm done. There it is. That's what they were asking for. This part here is the f of X, and then plus what f of 3 is, which is 3. I wish I'd chosen different numbers, so what f of 3 is and 3. So that ordered pair is 3, 3. Okay. And this is just be using a calculator. Again, you would write down what it means. So, and I wish they had used parentheses here. So f of X is you're going to square whatever X is. Whatever number you have for X, you're going to square it. So f of, what is it? 5.678 equals 5.678 being squared. You just multiply it by itself, or you use a calculator and hit the square button. That's what I would do. It's kind of tedious to multiply a 4-digit number by itself. Okay. Oh, I see what they did. Yeah, well. And then square root is using the square root. Okay. Using the square root function on the calculator. That is definitely something I can't do in my head. Okay. All right, we have different forms of a function. One is implicit and the other is explicit. We're all used to seeing the explicit form where it's y equals. You're doing something to x to find the y value. That's the explicit form. Something happens to x, I get y. Right. Here, this is the implicit form. I can find out what y is, but I have to do more than just putting a number in for x and then simplifying the expression. Now I have to put a number in for x and I solve for y. Here, since it's already solved for y, whatever I put in for x gives me the y value without having to solve the equation for y. Right? So if you have x and y on the same side of the equal sign, then it's an implicit form of the function. And usually with implicit forms of equations, you need to be careful to make sure that it is a function. If something's happening to y and it's not linear, in other words, the exponent on the y is not 1. If y has a square in it on it, or it's being square rooted or something like that, chances are it's not a function. So you want to go through and solve for y to verify it. All right, for each x in the domain of a function f, there is exactly one image of f in the range. However, an element in the range can result from more than one x value in the domain. That's what I've been saying, right? F is a symbol we use to denote the function. We can use other letters, you know, F, X, G, H, whatever. Depending, sometimes we use a letter that talks about what we're trying to find. We're trying to find diameter, so we use D of X. Okay, that it's so it all depends. Or trying to find distance. So D of X equals. It is symbolic of the equation or rule or like I said, definition of the function that we use to get from an x value in the domain to the range, to a value in the range. If y equals f of x, x is called the independent variable or the argument of x, and y is a dependent variable or the value of f at x. I will often say the value. What's the value of the function? Well, the value of the function is the y value you get. Okay. Now, the difference quotient. Unless you move on to take some form of calculus, this is probably the only time you'll ever see the difference quotient. Okay. The difference quotient is a process. You have f of x, and then you can find f of x plus h, where we replace x with the expression x plus h and simplify it. And then we put it in, and then we subtract what we get for x, f of x plus h, minus the original function, f of x, And we divide that by h, provided h does not equal 0. All right, we put that, we stipulate that h can't be 0 because dividing by 0 is undefined. And it's just the process. You're given a function and you're asked to find the difference quotient. It's just a lot of manipulation. All right. Oh, I forgot they give us this problem. Anyway. If f of x equals the square root of x plus 1, then I want to, and to find the difference quotient, I want to find out what f of x plus h is, which means I'm going to replace this x with this expression. So now it's going to be the square root of x plus h plus 1. And so now I have the square root of x plus h plus 1 minus, okay, so that was the f of x plus h. So that's this expression. And I'm going to subtract the original expression, square root of x plus 1, and it's all divided by h. Now we want to do something so our h comes out of the denominator. Okay. And what we're going to do here is if I have the square root of a minus the square root of b, and I multiply it by what's called the conjugate, which means it looks exactly the same, except it has a plus sign in between. So these two are conjugates because the first term in both of them are the same, the second term in both of them are the same, and we're adding in one place and subtracting in the other. So in other words, we have the sum and difference of the same two terms. Now, there's something that happens when you multiply things like that. If you remember from Algebra 1, if you have a minus b times a plus b, you wind up with a squared minus b squared. You wind up with the difference of two squares. Well, that's why we do this. We're going to multiply by that. So I get the square root of a being squared minus the square root of b being squared. So I end up with a minus b. So I'm going to do that so I can get rid of these square roots up here. So I'm going to multiply the numerator by its conjugate, which is the square root of x plus h plus 1 minus, no, plus, because it was minus, plus the square root of x plus 1. And because I multiply the numerator by something, I have to multiply the denominator by the exact same thing. Otherwise, I change the problem. So multiplying the denominator by the same thing is multiplying by 1. X plus h plus 1 plus the square root of x plus 1. All right. The numerator and denominator are the same, so it's a 1. So I'm multiplying by 1. When dealing with fractions, when you multiply by 1, you change what the fraction looks like, not what it is. Okay, so my denominator, I'm not going to use the distributive property here. I have h times the square root of x plus h plus 1 minus the square, plus the square root of x plus x plus 1, sorry. And what happens in my numerator, I get x plus h plus 1, the square root of it being squared, minus the square root of x plus 1 being squared. And when you square a square root, the square root symbol goes away. So my upstairs, so this came down to here. And so now I have, what do I have? I have x plus h plus 1 minus the quantity, because I'm subtracting what's in here, and what's in here becomes x plus 1, and I'm dividing by the same thing, h times, my denominator did not change. And there's a reason why I'm not using the distributive property down here, and you'll see why in a moment. So now my numerator, because I'm subtracting both the x and the 1, so that x becomes a minus x and that plus 1 becomes a minus 1. So now I have x plus h plus 1 minus x minus 1 divided by h times the square root of x plus h plus 1 minus the square, plus, I keep doing that, plus x plus 1. Well, in the numerator, I can simplify because I have like terms to combine. I have a positive x and a minus x. Those go to 0. I have a plus 1 and a minus 1. Those go to 0. And here I have a plus h, and that's going to stay up there all by its lonesome. So I'm going to have to change pages here. So my numerator is just h. My denominator now is h times the square root of x plus 1. X plus h plus 1 plus, I remembered it's a plus sign this time, x plus 1, square root of x plus 1. Now I have an h in the numerator and an h in the denominator as factors. So this can go to 1 and this goes to 1. So this just becomes 1 over, it's a weird looking 1, isn't it? So that's just 1 over the square root of x plus h plus 1 plus the square root of x plus 1. Now they're going to end up doing the same thing, but I don't think they show all the steps I did. Yeah, they didn't explain why they're using this. That these are conjugates, and this is what happened when you multiply conjugates together. Okay. And then they squared that and wound up with this. And then they subtracted that. Well, they didn't show what happened there. One way to look at what's happening there, here I have x plus 1 plus h minus x plus 1, right? I can group I can do the commutative property and switch their order here. So it's x plus 1 plus h. Well, let me do it the other way. I'm going to switch the order of the x and the h. So the h comes first, x plus h plus 1. 5 plus 3 is the same thing as 3 plus 5, so I can do that. And I'm still subtracting x plus 1. And because of the associative property with addition, I can group things as I want to. So I can group this as x plus 1, and I'm subtracting x plus 1. So I'm subtracting the same thing from itself, so that leaves me the h. I still just wind up with h in the numerator. The magic of math. I play with numbers all the time. Okay. Now to find the domain is what numbers can I use? Okay. So we always start with the all real numbers. And then we look to see is there a restriction? Are there numbers I cannot use? Okay. So like here, we have this function is a fraction. What number can I not have in a fraction and it still be a real number? And so it stays a real number. Right. What number we can't divide by? Well, we can't divide by 0. So that means the denominator, the x minus 2, cannot be 0. Well, if I add 2 to both sides, that means x can't be 2. So the domain here is all real numbers except 2. And there's a number of ways to write this, okay? I can look on the number line. And here I have 2, and it can be everything below, and it can be everything above, but it can't be 2. Now, one reason I do a number line is because this shows me how to write it as far as interval notation is concerned. Interval notation talks about going from the low to the high, the low to the left and the high to the right. So, yeah. Oh, I forgot about the numerator too. The numerator with the square root of 2x minus 6, 2x minus 6 cannot equal 0 or be less, no, cannot be less than 0. So we would add 6 to both sides. Well, that's a plus, isn't it? And I wrote it down as minus. That'll get me in trouble. And then you have 2x has to be less than a negative 6, or x has to be less than a negative 3, less than or equal to, because it can equal 0. So x has to be less than negative 3. Oh, is it less than? No, it has to be greater than. I'm sorry. Put the wrong symbol there. Has to be greater than, because it can't be negative. All right. But realizing it can't be 0, it can't be positive 2. So x greater than negative 3 and x not equal to 2 are the two inequalities that define this domain. Now, what they're showing here, this is set builder notation. So set builder notation talks about the set of all x such that x has to be greater than or equal to negative 3 and x does not equal 2. Okay. If you don't really understand what's going on here, we'll do it enough times that you'll start to see the pattern and understand what we're talking about. Okay, so we look, square root has restrictions on what values you can put under there. They have to be positive or 0. Non-negative, you can only have non-negative under the square root symbol, and you can't have 0 in the denominator of a fraction. X can be 0, but what x minus 2 cannot be 0. And so that's why we looked at x can't be 2 and x has to be greater than or equal to negative 3. So we put those two together for our situation. So I'm not even going to talk about interval notation. So that wasn't useful. All right. So to find the domain, you always start with all real numbers. And then if the equation has a denominator, you need to exclude any numbers that give the denominator 0. And if the equation has a radical with an even index, then you need to exclude numbers that cause the radicand, which is the number inside the radical, negative. So if we're talking about the fourth root of 3x minus 9, then I only want numbers in here that will make that expression non-negative, positive or 0. But if it was the third root of 3x minus 9, well, realize that the third root of -1 is -1. Because if I take three negative ones and multiply them together, I'll get -1. You can take the odd root of a negative number and still get a real number. It's just going to be negative. So if the index number is even, then you cannot have a negative number inside the square root symbol, so it has to be greater than or equal to 0, that radicand. So we talk about it being non-negative if it's positive and 0, because 0 has no sign. 0 is neither negative nor positive. Express the volume of a cube as a function of its side length. All right, if you have a cube, I'm cheating here because I have little squares here that can help me with this. If you have a cube and the length of one edge is S, how do you find the volume of a cube? Anybody remember that from their formula charts in high school? If you have a rectangular box, and it did it to me again. Sorry, folks. What I've realized what I'm doing is I'm hitting something while I'm writing that makes it happen. So we have the height, we have the width, and we have the length. How do you find the volume of a rectangular box? Anybody remember what that formula is?
Use length times width times height.
Length times width times height. Well, the same thing is true with a cube. But what do you know about the length, width, and height in a cube?
They're all the same.
They're all the same. So that's the side times the side times the side, which is S cubed. So what's the formula? So if we say we're going to take the formula for the volume of the cube is the side cubed. Well, to turn this into function notation, we're going to call the function v, and the argument is the length of the side, so the argument is s equals s cubed. So here we have it written. Here it is as a formula. Here it is as a function. Now the domain, why do they say the domain has to be greater than 0? S has to be greater than 0. Can you have negative length? No. Negative only denotes direction. The length is always positive. Direction negative sign means you're going in an opposite direction than the given direction. It's like on the football field. You gain 5 yards or you lose 5 yards. Gaining 5 yards is +5, losing 5 is -5. So the sign just denotes direction. I'm driving in reverse, so I'm losing distance, so I'm going in a negative direction. Because going forward is the positive direction. Okay. So that's why S isn't negative. But what about 0? Can I have a length that is 0? Yeah, it's awfully hard to build it. You know, well, that dimension is 0. Well, then how is it anything? If S is 0, then we're just talking about a point which has no length, width, depth, or volume. It's a location. Okay. Now, this is the end of section 1, I think. Form the sum, difference, quotient, difference, product, and quotient of two functions. So basically the sum is adding, so we're going to add two functions. The difference is subtracting, so we're going to subtract two functions. Okay, parentheses are your friend. And then product, again, parentheses are your friend. We're multiplying two functions together. And then a quotient. A quotient is a fraction. Fractions are division. Division is a fraction. So if it says quotient, you're doing division, which means you have a fraction. All that means is you have one function in the numerator and the other function in the denominator. Boom. Most times you're done. You just write it that way. That's the easiest one to do, and it's usually the one most people mess up on. All right. But now we're talking about notation. Okay. And from my point of view, this is just quite obvious that means we're adding two functions together. F of x plus g of x. The sum. Now, when it's written f minus g of x, we're subtracting the two functions. So it's going to be the f function minus the g function. It's in the same order as it is over here in the notation. Please realize if you're subtracting a function, you need to put that function inside parentheses. So you're telling everybody I'm subtracting everything in that function, not just the first thing. That's where a lot of people mess up on that part. Multiplying, again, parentheses are your friend. When it's written this way, f times g of x, and sometimes it's just written as fg of x. This means we're multiplying the two functions together. I prefer to use brackets around them because that means I'm going to take this, whatever function this is, and I'm going to multiply it by whatever function g is. So sometimes it involves using the distributive property or multiplying binomials together, or multiplying a trinomial times a binomial, or multiplying fractions together, where you do the multiplication appropriately. So it equals the same thing. And then the last one is a quotient. Quotient means you have a fraction. So you have f divided by g. So that's a quotient. So f over g of x, which is you're going to take the f function and put it in the numerator and take the g function and put it in the denominator. Easy peasy. Most times that's all you have to do. You don't have to simplify it, because sometimes you can't. If you can factor and then simplify, great. But most times you cannot. So examples. And of course, they give us fractions. Yeah. Can we do this in 5 minutes? Okay. Now, they want to do f plus g of x. So that means it's going to be 2 over x plus 3 plus x over x minus 4. When it's written this way, you want to simplify it to one fraction. And sometimes when you do that, it becomes not a fraction. So the denominator disappears, but it won't in this case. So we have 2 divided by x plus 3, and we're adding to it x over x minus 4. And to add them, we need to get the same denominator. The only way I can get the same denominator in this case is multiplying the two denominators together. So that means I'm going to multiply this denominator by x minus 4, and I'm going to multiply this other denominator by x plus 3. And the denominators I'm not going to multiply out, because I'm just going to leave it that way. But I have to multiply the numerators appropriately. Otherwise, if I just leave it this way, I change the problem. If I multiply the denominator by a number, I need to multiply the numerator by the same number. So I'm multiplying by 1. So I change what it looks like, not how much it is. So my denominator, I'm just going to write it as x plus 3 times x minus 4, or I could have chosen the x minus 4 times x minus 3. Using the commutative property, these are the same thing. So I just chose one of them. Now, here I'm going to multiply in by 2, so now I have 2x minus 8, and I'm going to add x times x plus 3, so I'm going to do x times x and x times 3, so I get x squared plus 3x. And since I'm adding, I don't need to worry about parentheses. If I was subtracting, I would need to keep the parentheses over here. And now I combine like terms. All right, I look, there's only one x squared, so I'm going to put that one first. I have 2x and I have 3x, so that gives me plus 5x. And then I have a minus 8. And my denominator hasn't changed. X minus 3 times x minus 4. Now I look to see, can I factor this? And it turns out I cannot, so I'm done. If you can factor the numerator after you simplified it, you factor it to see if there are factors from numerator and denominator that are the same, so they can go to 1 and disappear. So like instead of being 5 here, what if it was a 4? No, what if it was a 2 instead of a 5? So then you could factor it, but it still wouldn't work out. But if it was a minus, but then you could factor it, but in that case, there wouldn't be any factors the same. Oh, and I changed that plus sign to a minus sign. Oops. So we're done. Oh. So we're on slide 34, letter B. Okay. So we've gone as far as we need to go for the day. You should be able to, what is it? You should be able to get into MyLab and work the problems. And when they get to operations on the functions, when you're doing the algebra of the functions, adding, subtracting, multiplying, and dividing the functions, if you want to wait until after Thursday to get back into it, go ahead and wait, or go ahead and go through and try and figure out what they're doing there. And sometimes people can figure it out. The help can help you understand it and get beyond it. Or you can, again, you can wait till Thursday and we'll cover the rest of it. But I've had a number of people who like to work ahead, which is fine, because working ahead, for some people, working ahead, they can kind of sort of figure it out, but they're missing some key step. And so when we get to it in class, light bulbs go on. So I get blinded by all the lights going on, people understanding. All right. Unless you have questions for me, we're done for the day, and I'll see you Thursday. Okay. So unless you have questions for me, or you want to hang around to listen to any questions people might have, you're free to go at any time. I'm going to go ahead and stop the share because I'm being selfish. Okay.
Mr. Reed.
Yes.
I was just saying bye.
Oh, bye. Waving off camera. Here we go. Stick my hand up over here and wave, and nobody sees it but me. Oh, wow. All right. See you later. Gus, right? Oh, he's gone. Okay. Serena, you there? Or are you going to go? All right. I'm going to go ahead and call it quits for the day. Unless you have a question for me. Oh, okay. So now I say goodbye.